Hello everyone, myself N.Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the last class, we discussed about shear of closed section beams and in which we solve problems and which are subjected to shear loads, and then we solve shear center as well. So in the present class, we are going to discuss about deflection of open and closed section beams. So the learning outcomes in this module are students are able to analyze the deflections of open and closed section beams, and students are able to solve problems on deflection of beams. So as you know that when deflection of beams is concerned, and there are various methods are there to find the deflection and slope. For example, you got a double integration method, you got a moment area method, you got Macaulay's method. So many other methods are there, and strain energy method. So like that, but here what we are considering is we are trying to consider the deflection of open and closed section beams for a beam which is subjected to booms, and also which may be open or closed. So again, the structural idealization concept here we have to utilize. So by using that, the formulae will slightly modify, and let's look into that. So the deflection of open and closed section beams, and the formula is given by delta m, that is equals to integral L into integral of A sigma z1 into epsilon z0 into dA into dz. And now here, what is this sigma z1 and sigma z2? So as we know that sigma z is nothing but the direct stress distribution in any open or direct stress distribution in any open or closed section beam, and then epsilon z is nothing but direct strain, and now here you are seeing the suffixes, that is 1 and 0. Now the suffix 1 here refers to unit load, and suffix 0 is refers to the original load. So whatever the stresses and strains we calculate, so we have to calculate according to the original load and also according to the unit load, or it is also called as dummy load or virtual load. So it is also called as dummy load or virtual load. So what we are going to do here, it is first we are going to calculate the stress and strain according to the original load, and we'll write that as sigma z0 and epsilon z0, and then after the original load calculations are done, then we are going to remove this original load and replace it by a unit load, that is 1 Newton load, and then we'll try to calculate the corresponding stress with the unit load, that is sigma z1, and also the strain with the unit load, that is epsilon z1. Now, so usually when you try to solve the problems on this deflection, and when the strain energy is there, so you have the formula deflection is equals to dou u by dou p, that is the partial differentiation of total strain energy stored with respect to the force acting at point R. So that gives deflection at point R, and this, in other words, we get this integral 0 to L m square dx by 2 ei. So we usually used to take like this, m square dx by 2 ei. Okay, so now this m square, instead of this, what we'll write is the m bending moment due to original load and bending moment due to the dummy load, that is unit load, into dx by 2ei. So like that, we are going to modify the formula which we know from the strain energy method, and then we are going to write it here. So let's look into this one. So here we have sigma z1 and epsilon z0, the formula, and then sigma z, direct stress distribution formula we know, that is nothing but equals to my ixx minus mx ixy divided by ixx iyy minus I square xy plus mx iyy minus my ixy divided by ixx iyy minus I square xy. Now here what you need to do here, it is sigma z1, since you are calculating for 1 with respect to the unit load. Now you are going to replace my by my1 and mx by mx1 and my by my1 and mx by mx1. So rest of all it is same. Similarly, and if you try to write strain, so strain is nothing but that is equals to stress by Young's modulus. So 1 by E Young's modulus into stress, you can write the same equation, but while writing here, mx and my are replaced with mx naught and my naught. So my naught and mx naught. So as we discussed, this naught refers to the original load, and then the 1 refers to unit load. So that is what we need to understand. Okay, and once you get these expressions, you can substitute over here, and then the corresponding equation will be integrated around a particular area, and then again once again it is integrated for the total length, so that you can going to get the deflection of open or closed section beams. Okay, and so this is what delta m corresponding to bending. So delta m, whatever you're calculating, it is corresponding to bending of the beam. So the deflection due to bending, we can say in other words. So next one, delta s is nothing but the deflection due to shear, and the formula for this is nothing but integral 0 to L and integral over section q naught q1 divided by gt into ds into dz. So again q is the shear flow, so instead of q square, and then we are going to write q naught and q1, and again q naught is nothing but the shear flow due to original load, and then this one q1 is nothing but the shear flow due to unit load. Okay, so that we have to use the formula which we know for shear flow distribution either in open and closed section beams. So you have to calculate the shear flow due to original load and the shear flow due to the dummy load, that is unit load, and then you have to substitute here and integrate between the appropriate limits. Then you are going to get the shear deflection or deflection due to shear. Similarly, the third one, here it is torsion, and here also instead of t square gj by dx or dz, so here you got T naught into T1. Again, T naught is nothing but the torque due to original load, and T1 is nothing but the torque due to unit load. Okay, so sometimes in the question you may get only the bending alone, you may get in the problem, or sometimes bending in combination with shear also you may get. In that case, you have to calculate delta m as well as delta s. Sometimes you may get torque, that is the case of torque or shaft that he will give. So in that case, you have to calculate this torsional deflection or deflection due to torque. Okay, so this is the formula that we are going to use for solving the problems in deflection of open and closed section beams. Now let's try to consider one problem and let's look into that. So calculate the deflection at the free end of a cantilever beam of 2000 mm long, having a channel section identical to that of the previous example which we solved, and supporting a vertical upward load of 4.8 kilonewton acting through the shear center of the section. The effective direct stress carrying thickness of the skin is 0, while its actual thickness is 1 mm. Young's modulus and the shear modulus are given as 70,000 and 30,000 Newton per mm square. So he is asking to calculate the deflection at the free end of a cantilever beam. So if you try to remember this problem which we solved for the shear of open section beams in this unit only, structural idealization, and in which you got the shear flows, open section shear flows as Q equals to minus 6 Newton per mm or Q12, and Q23 equals to, you got minus 12 Newton per mm, and Q31 equals to minus 6 Newton per mm. Okay, these are the shear flow which we got through the previous problem. Okay, how did we got this one? And we calculated shear flow first distribution, and because of symmetry the formula reduces to minus S5 divided by Ixx and summation Ai Yi you got. Okay, summation Ei Yi you got, and then you calculated Ixx, moment of inertia for this, and which is nothing but 2 into boom area of this 1, and then followed by the y distance which is nothing but 100 and 200 mm square. So for this question he has given the boom area which is similar, that is equals to 300 mm square boom area. Okay, so you got 300 into 200 square. Okay, so that is for that 1, boom 1, and similarly for 1, 2, 3, 4 you are going to get same distance 200, 200, 200, 200. So again this is multiplied by 2, 4, and then you got the moment of inertia, and then SY is already given to you, that is 4.8 into 10 to the power of 3 Newton, and you can substitute, and when this one you may get 48 into 10 to the power of 6 mm power 4, and when you try to substitute this you get Q equals to minus of some constant into AIYI, and then you substitute the respective 1, 2, 3 boom areas as well as its y distances, then you got this Q1, 2, 2, 3, 3, 1. Okay, but that's not our problem. So this is what we have done in the previous class, what we have done. And now here he asked to calculate the deflection of the free end of the cantilever beam. So he considered a beam like this, okay, and then he mentioned that it's supporting vertical upward load of 4.8 kilonewton. So somewhere here vertical load is acting, and that is shown here, okay, and it is acting through the shear center. So let us assume that since the given section is channel section, and we know that the channel section is symmetrical about horizontal axis, and therefore the property of the shear center is that it lies on the axis of symmetry. So it may lie anywhere on the axis x-axis, but let's assume that it is acting at this point, and let that point be shear center through which a vertical shear load SY is acting, that is 4.8 kilonewton. So let us assume the distance from here to here, it is XS, that is distance of shear center from web to 3. Let us assume it as XS. Okay. So now coming to this, but the question here it is asking to calculate the deflection. So you might have seen that, you know, the deflection curve, since the load is applied here, so the deflection curve goes like this, the deflection curve, and this is the deflection what is asking to calculate, the deflection. Okay, and since he has given only the load, that is vertical load, that is given SY, so you need to calculate deflection at this free end. Okay, so that, and even he has given the span of this cantilever beam as 2000 mm, that also you can mark here, and the cross section of this is shown here as a channel section with the booms. Okay, so that is the diagram. So let's look into this problem. So now, and he also mentioned that the effective direct stress carrying thickness of the skin is 0. So effective direct stress, that is TD, is equals to 0, and then the actual thickness, that is T, is equals to 1 mm, that he has given. Okay, so now if you try to look it into the formulae for this one, since the load is applied through the shear center and there is no twisting of the section, and now the total deflection delta is equals to given by delta M plus delta S. Okay, the total deflection is the combination of deflection due to bending plus deflection due to shear. And let's try to put it into the formula. So the deflection, that is total deflection delta T, that is equals to deflection due to bending, and usually in strain energy method we use the formula integral 0 to L m square dx by 2 EI, but now the formula is modified, and then it is given as m, instead of m square we got mx naught into mx1 into dz divided by E into Ixx, plus, and the shear deflection integral 0 to L integral over the section q naught q1 by gt into ds into dz. So this is the formula for the deflection, which is a combination of bending as well as shear. So let us assume this as equation number 1. Now in this, so whatever the parameters that we have here, mx naught, mx1, q naught, q1, so these we need to calculate separately, as we already discussed that that 0 refers to the original load, whereas 1 refers to the unit load. So you have to calculate bending moment due to original load as well as unit load, that is mx naught and mx1. Similarly, the shear flow due to original load and the unit load, that is q naught as well as q1. And then you can substitute in the formula rest of all the things that he has given. Thickness he has given, G, modulus of rigidity he has given, Young's modulus is given, and moment of inertia just now we calculated and we got it as 48 into 10 to the power of 6. Then the only calculations what we need is these calculations. So once we know these calculations, and then you can substitute in the formula and integrate between the respective limits, and you can come to know the deflection of open and closed section beams. In fact, in this problem it is open section beam. Okay, so now it's coming to this one, mx naught. Let's try to find out this mx naught, which is nothing but bending moment due to original load. Okay, and we have already assumed a cantilever beam in the here, and so what we do here it is, let us assume that let's consider a section Z. Since the total distance is, total span is nothing but 2000 mm, let us assume a section, and at this section let's try to write the bending moment. Okay, so therefore, so the bending moment at this section mx is equals to load, and since it is going to give 4.8 into 10 to the power of 3 is the load, and into this z is the distance, so that the rest of the distance will become 2000 minus z. So 2000 minus z, and then you can consider this is hogging moment, and then you can write minus sign. So therefore, so therefore you can write this mx naught as minus 4.8 into 10 to the power of 3 into 2000 minus z. So that is nothing but the bending moment due to original load. Now mx1, the bending moment due to unit load, you are going to get, just replace this original load 4.8 kilonewton by a unit load, that is 1 Newton. Now this has been replaced and rewritten here, then you can get mx1. So mx1 equals to minus 1 into 2000 minus z. Similarly, the formula for shear flow that we have seen earlier, that is Q equals to minus Sy by Ixx summation, instead of Ei, let's try to write Br yr. B is nothing but for boom area. Instead of A, we assume for normal area for preparing plane sections. Whereas when you have booms, you can replace that A by B, which gives the boom area, Br yr. So Sy is known already, that is 4.8 into 10 power 3. So that we are going to write here. So minus 4.8 into 10 power 3 Ixx summation R equals to 110 Br yr. Now that is Q naught. So Q1 is nothing but what? Replace this original load by 1. Okay. And then you are going to write Q1 as it is. So this is how we'll try to find out mx naught, mx1, Q naught, Q1. So once we get all these things, let's try to substitute all these in this formula. Okay. And let's try to do the calculations. Now, when you try to calculate here, and you get a relationship, because Q naught you can get right in terms of Q1, because only the 4.8 10 power 3 and this is 1 is only the rest of everything else is same. So therefore Q1 you can write it as Q naught divided by 4.8 into 10 to the power of 3, and then let's try to evaluate the bending deflection first, that is delta M. First let's try to evaluate. So evaluating the bending deflection, and we had bending deflection, the formula integral 0 to L 0 to 2000 mm, and then mx naught. So mx naught is nothing but 4.8 into 10 power 3 into 2000 minus z, and mx1 is nothing but minus 1 into 2000 minus z. So anyway, minus and minus, here you're going to get plus. Okay, and in fact for this problem, and the bending moment, here you will get sagging moment, because the beam bends in this manner in which you find the curvature and in which you get positive bending moment. So here mx naught also positive and mx1 also positive, that you have to consider according to the sign conventions. So when you try to multiply this, so you're going to get 4.8 into 10 power 3 2000 minus z into 2000 minus z, you're going to get 2000 minus z whole square divided by Young's modulus is 70,000 and moment of inertia is 48 into 10 power 6. Okay, so when you try to rest of all these things are constant, and you can integrate this 2000 minus z whole square. So you can take it as 2000 square plus z square minus 2 into 2000 into z. So that is 4000 z, and then you can integrate this, and you are going to get 2000 whole square into z minus z square. You are going to get z cube by 3 minus 4000, and z becomes z square by 2. Okay, and then you can substitute the limits, upper and lower limits, that is 0 to 2000, and you are going to get here and divide it by 70,000 into 48 into 10 power 6. and then you're going to get the deflection as 3.81 mm. Okay, so this is what the bending deflection. So the shear deflection 1 by gt, and then you can substitute for Ixx, and you can multiply by the shear flow, and you can multiply these two equations, that is minus 4.8 into 10 power 3 divided by Ixx integral summation r equals to 1 to n br/r, and minus 1 by Ixx r equals to 1 to n br/r, that you can substitute here, and then you are going to get that q square, q12 square, that is 6 square into 200 mm, and the 12 square into 400 mm, that is q23, and then this is 6 square into 200, that is q34. So the perpendicular distance you can consider, and then you're going to get the shear deflection as 1 mm. So once you get the shear deflection, the total deflection is the summation of deflection due to bending and the shear deflection, which you're going to get 1 plus 3.81, that is equals to 4.81 mm in a vertically upward direction, and that we have seen here. So this is a shear deflection. Okay, that what we got, that is 4.81 mm. So this is how we try to solve the problems on deflection of open and closed section beams. Thank you everyone. So in the next session, we are going to discuss the problems on shear center or shear flow.